Hi everybody. I wanted to introduce you to my good personal friend, the excitation table. Oh, how exciting. The excitation table is going to drive the um, formulation for flip-flop conversion. And what we're going to do is we're going to convert stuff into an SR flip-flop. And we'll start off by writing the truth table for the SR flip-flop. And we'll write the excitation inputs on the far left, and then the present state to the right. Then we'll enumerate all inputs and all present states. And then what we'll do is draw out the next state. We'll draw out the JK inputs that we need. Then we'll draw out the toggle inputs that we'll need. And then we'll draw out the D inputs that we'll need using our friend, the excitation table. And just to make it neat, I think what I'll do is I'm going to group by function. And we'll call this the hold state, the reset state, the set state. And in this particular case, we'll have the you can't do that state because you don't want your SR latch to have both inputs equal to 1. And now what we'd like to do for the hold state is show how the present state is held. Here we reset, here we set, and here we just don't care. And so the don't cares, that's kind of interesting. I would expect them to propagate in to the JKs. But in any case, let's move the excitation table a little bit closer. And what we'll do is we'll just read off the row from 0 to 0. I see 0x, 0, and 0. So I'm doing all the flip-flops in order. Then the next one is, let's see, 0, 0 is here. So I'll do those as well. Then I see a 1, 1. That's going to be x, 0, x, let's see, x, 0, 0. And then 1. Got to be careful to keep these things in line. You don't want to try and implement an SR flip-flop with an SR flip-flop. And if there's any more 0, 0s, I'd put them in there, but there aren't. Then I got 1, 0, and that's going to be x1, 1, and 0. And I got 0, 1. That's going to be 1x, 1, and 1. Then I got over here 1 to 1, and that's going to be x 0, 0, and 1. And if it really is a don't care, then I guess we don't care about any of these either. And that makes life a little bit easier for us. Now if I compare this line here for J against the set, it kind of looks like set. In fact, J is equal to set. So if you just set J equal to set, you're all done. And then if by I compare K to the rows in here, could K be equal to reset? Indeed it is. So K equals R. So to turn a JK flip-flop into an SR flip-flop, you just set J and K equal to S and R. What about T? Well, if we take a look at T, it looks like we might need to formulate some kind of a K-map. So for that K-map, the inputs will be S and R with Q on the side. And this will give us T equals as a function of S and R. And so now we have, let's see now, 0, 0, 0, 1, 1, 0, XX. And for a loop, I think we can do something like this. And so now we have T equals, this does not change, so that's R. And that's going to be Q. And looks like this does not change, so that's S, and that's Q prime. And now for the D flip-flop, we can move our excitation table out of the way now. Let's take a quick look at the inspection here. I think we're going to have to do another K-map. Oh, I got a nice big loop in here. So what that tells me is that D is equal to S or, and we're going to loop in through here, R prime Q. So it looks to me like I can make a D flip-flop with S ORed with R prime Q. I'm making an SR flip-flop with the D flip-flop, or I can make the SR flip-flop with a T flip-flop. Or I can make an SR flip-flop with a JK flip-flop. And now we've got a way to use an SR flip-flop. Oh, and you can go the other way too. Scratch that out, because that's not what we were looking for. So we were looking for, this is what we're looking for an SR flip-flop, and we want to use any of these flip-flops. And so you can look for any flip-flop and fabricate it from any other flip-flop using this technique. Thank you.